Today we're going to talk a little bit about Ohm's law in parallel. Today we're going to start with a quick review of parallel circuits. Then we're going to talk about what is Ohm's law in parallel, why is it important, how do we actually use it, how does it work, and then we'll do an example of Ohm's law in parallel. And then finally we'll do a recap of what we covered today. So let's get started. Let's start with a quick review of parallel circuits. Remember, we said a parallel circuit looks like this. The beginnings of all of the components are connected to each other, and the ends of all the components are connected to each other. The parallel resistance formula looks like this. 1 over the total resistance equals 1 over the first resistance plus 1 over the second resistance plus 1 over the third resistance, and so on. And what this means is that the total resistance of the circuit is less than the resistance of any one element in the circuit. Remember, we said that this works because when you have a parallel circuit, the electricity has more places to flow, so that it's easier for the electricity to flow through a parallel circuit than if the electricity had to flow through just one element of that circuit. Now let's talk about what is Ohm's law in parallel. Well, imagine that you have a parallel circuit like this. You've got several resistors in parallel, and you've got a power supply that is supplying voltage to them. Ohm's law allows us to find the voltage and current for each of these elements. Why do we care about Ohm's law in parallel circuits? Well, many circuits include parallel elements, and using Ohm's law with these circuits allows us to analyze existing circuits and also design our own. So Ohm's law is a really important tool. So how do we actually use Ohm's law in a parallel circuit? Well, the basic strategy is to start by finding the equivalent resistance of the circuit using our parallel resistance formula. Once we know the resistance and the voltage for the circuit, then we can find the total current for that circuit using Ohm's law. Then we can remember that the voltage is constant along any wire. And since parallel circuits have two parallel wires, we can use that knowledge to then find the current through each element in that parallel circuit. This might sound a little bit complicated, so let's do an example and see how it actually works. Suppose we have a circuit that looks like this. We have an 80 volt power supply, two 40 ohm resistors, and one 20 ohm resistor, all in parallel. And suppose that we wanted to find all of these quantities for this circuit: the total voltage, the total resistance, the total current, and then the voltage and current for each resistor. Before we get started, let's look and see if there are any of these quantities that we can write down without having to do any math. The first one I see is that the total voltage is just the voltage that's coming from the power supply. So we can write that down right away. So that's 80 volts. Then what we want to do is we want to find the equivalent resistance for this circuit. So we can do that using the parallel resistance formula. We say 1 over R total is 1 over R1 plus 1 over R2 plus 1 over R3. So in this case, that's 1 over 40 ohms plus 1 over 40 ohms plus 1 over 20 ohms. So R total comes out to be 10 ohms. So this circuit is equivalent to a single circuit with just 10 ohms of resistance, just like is drawn at the bottom of the page there. And we can write down that resistance over in our total resistance column. Now that we know the total resistance for this circuit, we can try and find the total current. If we know the resistance and the voltage, then we can use Ohm's law to find that current. So Ohm's law says that the total current is just the total voltage over the total resistance. So in that case, that's 80 volts over 10 ohms. So that comes out to be 8 amps. That means we have 8 amps flowing through the circuit there. And we also have 8 amps in our column of answers. All right. We can also write that we have 8 amps flowing through our circuit on our original circuit there, And we have 8 amps flowing out of the power supply, and power supplies always have to have the same amount of current flowing out and flowing back in. So we can also write down that we have 8 amps flowing back into that power supply. Once we have that total current, we have to find some of these other quantities. So let's think about the voltage here for a minute. Have we can choose any point on our circuit and arbitrarily call that 0 volts, and then every other point can have a voltage relative to 0. So oftentimes the negative side of the power supply is chosen to be 0 volts. So let's call that 0 volts right now. We'll make a little mark on our page to remind ourselves. That point is 0 volts. Now remember, the voltage along any wire is constant. So if we have 0 volts at that point, we also have 0 volts at that point, 0 volts there, and 0 volts there. 0 volts all along that whole wire. The voltage does not change along a wire. Now we can look at our power supply and see that that's an 80 volt power supply. That means that one side of the power supply is 80 volts higher than the other side. We just said that the bottom part of our power supply is at 0 volts. So if we go up by 80 volts, that means that the top of our power supply must be at 80 volts. So we've got 80 volts there. Now remember, again, the voltage is constant along any wire. So if we have 80 volts over there, we also have 80 volts there, 80 volts at the top of the R2, and 80 volts there. Okay, so what this shows us now is it shows us the voltage difference across these resistors. If we look at R1, we see that we have 80 volts at the top of it and 0 volts at the bottom, so that is an 80 volt difference across R1. We can say the same thing for R2. There's 80 volts at the top and 0 at the bottom, so there's 80 volts across R2, and the same goes for R3. So now we can write down those voltages over in our column of answers. 80, 80, 80. So all of those resistors have 80 volts across them. And now, once we know the voltage across those resistors, we can also figure out their currents using Ohm's law. So for R1, we know the voltage and the resistance, so we can use Ohm's law to figure out the current. So we say I through R1 is V over R, VR1 over R1. So that is 80 volts over 40 ohms. So that comes out to be 2 amps. So we can draw 2 amps on our diagram, and we can also write down 2 amps in our list of answers. Now let's look at this current for a minute. We know that we have 8 amps flowing out of the power supply, and 2 amps, 2 of those amps are flowing down through R1. So the rest of the current has to be flowing this way. So that means that we have 6 amps flowing this way. Now let's try and figure out the current through R2. Well, it has the same resistance as R1 and the same voltage as R1, so therefore Ohm's law tells us it must also have the same current as R1. So we can say that we have 2 amps flowing through R2, and then we can write that down in our list of answers over there. So if we had 6 amps flowing this way, and 2 of those amps flowed down through R2, that means that we have the remaining amount of current flowing this way. So that means we have 4 amps flowing that way. Now we can use Ohm's law to figure out the current through R3. So again, we say I is V over R, so IR3 is VR3 over R3. So that's 80 volts over 20 ohms. So that comes out to be 4 amps. So we can draw that on our diagram and also write that down in our list of answers. Now there's another way we could have done this also without having to use Ohm's law. We could have just said, well, there's 4 amps flowing through this part of the circuit, and it only has one path to follow, so all of that current has to go through R3. So we know that there has to be R3, or 4 amps going through R3, even without doing Ohm's law. So now we have all of the answers that we were looking for, but let's follow the current around through this circuit just to see what happens with it. So we know that we have 4 amps flowing through R3 here, and that current has only one path to travel through at the bottom of this circuit, so there has to be 4 amps flowing along this wire also. Now this 4 amps meets up with the 2 amps that was flowing through R2, and when they join together, they create 6 amps flowing through this wire here. Then this 6 amps meets up with the 2 amps that were flowing through R1, and when they combine, they create the 8 amps that we knew was going to be flowing back into our power supply. So that's how the current flows around this circuit. Now let's take a look at this circuit and see what we can notice about it. In all parallel circuits, the voltage is the same across each resistor. So we can figure this out because, remember, a parallel circuit has a wire that attaches the top of one resistor to the top of every other resistor, and we said that voltage is constant all along any wire. So there's going to be a constant voltage along the top of the circuit, and the same goes at the bottom. The bottom of one component is connected to the bottom of every other component, and so there is a constant voltage along the bottom as well. So the voltage difference across one resistor is going to be the same as the voltage difference across every other resistor in a parallel circuit. So in all parallel circuits, voltage is the same for each resistor. But we see that current may be different in each resistor. Here we have 2 amps, 2 amps, and 4 amps. So we have different currents in different resistors. When the resistances are the same, then the currents are the same, but if the resistances are different, then they have different currents. And finally, the sum of the resistor currents equals the total current. So remember, our total current is the current flowing out of the power supply, and that's 8 amps here. And if we look at our resistor currents, we see we have 2 plus 2 plus 4. So that gives us a total of 8 amps. So the sum of the resistor currents equals the total current flowing out of the power supply. Now let's briefly recap what we learned today. Ohm's law lets us find the voltage and current for every resistor in a parallel circuit. Knowing these voltages and currents allows us to analyze existing circuits and also to design our own circuits. The basic strategy for using Ohm's law in a parallel circuit is to find the equivalent resistance for that circuit, then find the total current in that circuit, and then find the current for each element. And remember, the voltage for every resistor in a parallel circuit is constant. The voltage is always the same as the power supply voltage. So that's a little bit of information about using Ohm's law in a parallel circuit. Thanks for watching this video. I hope you enjoyed it, and I look forward to seeing you next time.